Okay, so we will start today's class. Okay, so today we are going to start a chapter called Chemical Equilibrium, right? So this is a new chapter that we are going to start today. I hope that all of you have gone through the videos of this chapter, because I've told you it will be better if you watch the videos first before attending the class. Okay, right? If not, please go and watch the videos of next topic. Okay, now when we talk about this chapter, chemical equilibrium, right? First thing that comes up in our mind, right? What is this equilibrium? The first question that you should ask yourself: what is the meaning of equilibrium? Tell me, anyone, what is the meaning of equilibrium? Can anyone tell me what is the meaning of equilibrium? Tell me. So I can say that equilibrium means no actual change. Okay, no actual change in the state of any object or any reaction or anything. Okay, right? Yeah, so most of you are answering with respect to force, right? So you can say that equilibrium is a state. Equilibrium is a state where driving force is equal to opposing force, right? Right, everyone? Okay, according to what you have studied in physics, so you can say that equilibrium is a state. First of all, it's a state, right, at which the deriving force is equal to opposing force, right? Okay, or there's no net change in the reaction, okay, or no net change in the process. Yes, right, everyone? Okay, so see, when we talk about chemical equilibrium, so obviously we talk about chemical reaction. Okay, we talk about chemical reaction. Now, when we talk about chemical reaction, first we have to understand the different type of chemical reactions. Okay, now by the definition of equilibrium, we know that by the definition of equilibrium, we know that it would be a state while the reaction is carried out, right? It will be a state at which there will be no net change, okay, right? No net change in the parameters. The parameters can be anything, right, everyone? Tell me, right? Okay, okay, everyone. So I guess this is understood by everyone. What's the meaning of equilibrium? Okay, now since it is chemistry, right, we are talking about chemical equilibrium. So we have to study the chemical reactions, right? We have to study chemical reactions. Now, first of all, before starting the chemical equilibrium, we should know what the different type of chemical reactions, right, everyone? Okay, so see, when we talk about chemical reactions, okay, so there might be many types of, or there are many types of chemical reactions depending on other factors. So see, we have a list of chemical reactions. The first is on the basis of state. Okay, now we know that what's the meaning of state? The meaning of state is phase. Okay, right? The meaning of state is phase. Okay, everyone, I'm just turning out my video so that you can just. So yeah, so we will start now, right? So I can say that on the basis of reaction, okay, phase, we have two type of reactions. First, homogeneous reaction, and second, heterogeneous reactions. Okay, so now when we talk about homogeneous and heterogeneous, we have studied in class 9. Homogeneous means same phase, right, everyone? Homogeneous means same phase, means the phase of both reactant and product should be same, right? When you talk about phase, it is either solid, liquid, or gas. So I can say that if both product as well as reactants are in same phase, then the reaction is called as homogeneous reactions. Okay, now if any one of the reactant or product is in different phase, for example, see this, we have a reaction in which zinc is solid, carbon dioxide is gas, zinc oxide is solid, and carbon monoxide is gas, right? So if any one of these four components, right, anyone is in different phase, then it is called your heterogeneous reactions. Okay, so this is on the basis of physical state. Now on the basis of direction, in thermodynamics we have studied about reversible and irreversible reactions. I hope all of you remember reversible and irreversible reactions, right everyone? Okay, yes. Okay, everyone. So obviously we'll talk about reversible and irreversible reaction. I think that I need not to explain what is reversible reaction, what is irreversible reaction. I hope all of you remember that reversible reaction is a reaction in which reacting is converted into product as well as product is converted into reactant. Okay, so the reaction is carried out in two ways, forward as well as backward. Okay, now in irreversible reaction, reaction is carried out in only one direction, which is a forward direction. Okay, now when we talk about reversible reaction, so there will be a point at which the rate of forward reaction will be equal to rate of backward reaction. Yes or no? Right? There will be a point, okay, at which the rate of forward reaction, okay, means the speed at which the reactant is converted into product is your rate of forward reaction, will be equal to rate of backward reaction, which is the rate at which the product is converted back into reactant. Okay, so I can say that at that point, the rate of forward reaction will be equal to rate of backward reaction, and the reaction is in equilibrium. Got it, everyone? Okay, so I can say that equilibrium will be attained only in reversible reaction. Equilibrium will not be attained in irreversible reaction. Okay, everyone? So if I ask you, what is the condition for a reaction to attain equilibrium? Tell me, what would be the condition? Everyone, what would be the condition? I'm audible, everyone? I'm clearly audible, right? Yes. So first and foremost condition, reaction should be reversible. Okay, that's it. Reaction should be reversible. Okay, that's the first condition, right? Okay, everyone? Okay. Second, when we talk about reversible reaction, obviously it should be in closed vessel. That's your second uh, condition, right? Yeah, Gibbs free energy. So Gibbs free energy will be zero when it is in equilibrium. Okay, that's the consequence. It's not the condition. Okay, okay, everyone. Now, third is on the basis of speed. Now, when we talk about on the basis of speed, we have fast reactions and slow reactions. This is just the definition, right? When any reaction is fast, it is called as fast reactions. When any reaction is slow, it is called a slow reaction, right? That's totally the speed. Okay, right? Now, we have also already studied many types of reactions. Okay, so we are just talking about the reaction that we are going to study in this chapter. So on the basis of heat, we have exothermic reactions as well as endothermic reactions. So we know that if by any reaction, if any reaction is carried out, if energy is released, okay, if energy is given out, then it is your exothermic reaction. And if energy is taken or absorbed, then it is your endothermic reaction. Okay, everyone, right? Okay, so I guess that is the basic idea. Okay, right? Now, when we talk about chemical equilibrium, reactant is converting me to product. Okay, so there's a chapter ionic equilibrium as well as chemical equilibrium. So you might be thinking that what is the difference between these two chapters? Trust me, there's no difference between those two chapters. The only difference is components. Okay, when we talk about chemical equilibrium, we will generally talk about molecules. Okay, right? We will generally talk about molecules or compounds. But when we talk about ionic equilibrium, we will talk about ions. As simple as that. Means when we talk about chemical equilibrium, the reactants and products would be my compounds as well as atoms or molecules, right? Which is non-polar, okay, or non-ionic reactants, okay. But when we talk about ionic equilibrium, we will have ionic components. As simple as that, right? Otherwise, the process definition, everything would be same. Okay, everyone, right? So that is the difference between ionic and chemical. Okay, now first we will see what is equilibrium and what is the change. Now just think about this, right? When we talk about equilibrium, so we have a reaction, okay? Just see this. We will have a reaction A, okay? A will convert into B, right everyone? A will convert into B, yes or no? So just suppose this reaction is reversible, which means when A is converting into B, B is also converting into A, right? Okay, B is also converting into A. So this is the representation of equilibrium reaction. So we should have a both side arrow. Okay, now suppose we started with 10 mole of A. Just imagine we started with 10 mole of A. So initially, what would be the number of moles of B? Tell me, everyone. Tell me. Initially, when the reaction started, what would be the number of B? 0, obviously, right? 0. Yes, very good. Okay, very good. Now, as the time passed, right? As the time passed, it will become 1. It will become, sorry, it will become 9. It will become 1, right? It may become 8. It will become 2. Okay, it will become 7, it will become 3. Okay, right? It will become 6, it will become 4, right? But again, if 6, 4, 6, 4, right? Means after this state, right? Even though the time is changing, right? The concentration is not changing. What is the meaning of this? Tell me. What would be the meaning of this? Can you tell me what will be the meaning of this? It means that after this point, 1A is changing into 1B. At the same time, 1B is changing into 1A. Yes or no? One atom of A is changing into B, as well as one atom of B is changing into A. Right? Yes, everyone? Okay? Means rate of change of A to B as well as from B to A is same. Okay? So I can say that after this point, when we have 6 moles of A and 4 moles of B, the conversion rate of A to B as well as B to A is equal. Means 1 mole of A is changing into 1 mole of B and 1 mole of B is changing into 1 mole of A. Now this state is called as equilibrium. Got it, everyone? This state is called as equilibrium state, where the rate of forward reaction is equal to rate of backward reaction. Okay, right? Understood, everyone? Tell me. Yes? Anyone have any issue in this? No, right? Everyone is getting it now. Everyone is getting it. It's very easy. Okay, very good. Now, just try to see this. Okay, just try to observe that on the graph. So suppose we have a concentration versus time graph. Concentration versus time graph. Now, we know that initially we have some amount of reactant. So this is your amount of reactant, right? It will have some amount. We know that amount in chemistry is termed as concentration. Okay. Now it can be pressure also, we'll see. Okay, but here I'm taking concentration. So as the time passes, what do you think? The concentration of product as well as reactant will change, right? Yes, agree. The amount of, right, or the concentration of reactant and product will change, right, everyone? So obviously the concentration of reactant will decrease, yes or no, right? If you have 10 chapatis in the morning, right, so obviously you will eat some chapatis in lunch, some chapatis in dinner, right? So it will decrease, yes or no, right? It's basic common sense that will decrease. Okay, right? Now obviously if you eat chapatis, you will gain energy, yes or no? You will gain energy, right? If you eat more chapati, you will have more energy. So in same way, if a reactant is getting consumed, product will be formed. Okay, so see the graph, right? See the graph. Okay, the reactant is decreasing, the concentration of reactant is decreasing, and concentration of product is increasing. Now we know that when we talk about graph, the slope represents rate, yes or no? Tell me. The slope represents rate, yes? So if you see at this point, if you see at this point, after this point, don't you think that the slope of both reactant products are equal? Tell me, right? Don't you think that the slope of both product as well as reactant are equal, right? According to the graph? Yes. So what's the meaning of that? It means it achieved equilibrium. Yes or no? Tell me, yes or no, right? Okay, very good everyone. So I guess you understood what is the equilibrium state, how it is represented graphically. Okay, right? Okay, now just think about this. Just think about this. Okay, just think about this. If we have open container, just think about this, that if we have open container and if some product escapes, okay, then is it possible to achieve equilibrium? Is it possible to achieve equilibrium? No, right? Okay, this is basic common sense. No, this is basic common sense, right? So I can say that equilibrium can only be achieved in closed vessel. Okay, right? Closed vessel. Okay, because if it is carried out in open vessel, okay, then the reverse process will not take place because some component can escape. Okay, right, everyone? Okay, very good. So we studied that. Okay, rest we have also explained that equilibrium is reversible in nature. Now, this is statement, right? This is a very important statement. Okay, this is a very important statement that equilibrium is dynamic in nature. What is the meaning of dynamic in nature? Now tell me, at equilibrium, suppose I'm having again reaction A gives B. At equilibrium, this will be 6, this will be 4, suppose. Now, will reaction stop? Tell me, will reaction stop? Yes or no? Will reaction stop? No, right? Okay, but if you observe the change, there will be no change. Okay, but the reaction is still carried out. Okay, it's just that the rate is equal, so that if we as an observer will see the concentration, right, we will feel that there's no change. But in reality, A is converting into B and B is converting into A. You right, everyone? Now this is called as dynamic nature. Okay, even though there's no net change, the process is carried out at each and every moment. Okay, got it, everyone? So it's like just imagine a tank, a water tank. Okay, so if you have a water tank, right, water is pouring in as well as if water is pouring out. If the amount of water which is pouring in is equal to amount of water which is pouring out, okay, then the level of water will not change. Yes or no? Tell me, the level of water will not change? Yes. Okay, but still water is changing, right? The water is changing now, right? The old water is going out and new water is coming in. Yes. Okay, so that process is called as dynamic process. Okay, everyone, I hope what is the meaning of dynamic in nature, right? Okay, now we will observe the graph. Okay, right? We will observe the graph. See, now we will see what can be the different type of graph for equilibrium. Okay, now see this, right? This we have already observed, so this is A. Okay, okay, so this is B. This is C. Now tell me, out of these three, which reaction is equilibrium reaction? Tell me, out of these three, which reaction, right? Which graph represents equilibrium? This is concentration, right? This is concentration, this is time. Tell me, which reaction represents equilibrium? A, B, or C, or all, or A, B? Yes, very good, everyone. So all the three represents equilibrium, right? All the three represents equilibrium. Yes, very good. So most of you are right. Okay, all the three represents equilibrium, right? The only difference is the concentration. Yes, all the three. Okay, right? Just think about this here, right? Okay, just see this. Okay, so I can see that at this point, right, the rate is equal. At this point, the rate is equal. After this point, the rate of reaction of both A and B is equal. So obviously they will be in equilibrium. Okay, right? They will be in equilibrium. Now, what is the difference between these three reactions? Okay, so the reaction, right? Just try to understand the graph here. Okay, so here I can say that the concentration of A and B are changing, yes, but they will be equal at a point before equilibrium. Okay, everyone? So there will be, it is not necessary that the concentration of reactant and product are equal at equilibrium, right? That's what we have to understand. That's what these three graphs tells us, that it can be equal, it may be unequal, right? Okay, so see, in case of first reaction A, the reactant and product, the concentration of reactant and product is equal at a point which is before equilibrium. Yes or no? Tell me. Yes or no? Right? Okay. Now, when you talk about second graph, okay, to see the second graph. In second graph, I can say that at equilibrium, the reaction, right, or the concentration of both react and product are equal. Yes? Yes, everyone? Right? So in second reaction, you can say that, okay, yes, the concentration of both reaction and product are equal at equilibrium. Okay, because they have same concentration. What about C? Okay, right? C. Now C say that they will never be equal. The concentration of a reactant and product will never be equal. Okay, so yes, equilibrium never say that your concentration should be equal. Okay, it just say the rate should be equal. Got it, everyone? Got it? Right? So I hope you understood all the three graphs. Yes? Okay. Very good, everyone. Okay, very good. So see this reaction, okay, this step is your second case that I have explained. Okay, now obviously we have different type of equilibrium. We have thermal equilibrium, mechanical equilibrium, physical equilibrium that we have studied in physics. Okay, in chemistry also you have studied thermal equilibrium. But in this chapter we will be talking about chemical equilibrium. As simple as that. Okay, right, everyone? Got it? Yes? Anyone have any issues? No, right? Okay. Now let's discuss each and every equilibrium in a brief. So the first was physical equilibrium. Okay. Now when we talk about physical equilibrium, what is the meaning of physical equilibrium? When we talk about physical equilibrium, it means the state, right? The reactant and product might be in different state, but they will be in equilibrium. The best example is melting of ice. Okay, right? When ice melts, it is in equilibrium at 0 centigrade, right? It will be equilibrium with liquid water. Yes or no? Tell me. Yes or no? Right? So that's a case of physical equilibrium. Okay, right? Or when we talk about vaporization, okay, when you talk about vaporization, in that case also, I can say that in that case also, liquid is in equilibrium with vapor. In case of melting or freezing, liquid is in equilibrium with solid. Okay, everyone. So I hope this is very clear. We have already studied this in class 10th. right? Physical changes, chemical changes. Okay, okay. So we'll be talking about this in chemistry. Okay, this is again individual solid phase to vapor phase to solid phase, right? I hope all of you remember sublimation, condensation, vaporization. Yes, okay, okay, everyone. So next is characteristics of chemical equilibrium. See, physical equilibrium, I just said, right, in which the phase is changing. The phase of reactant is different than that of the product, but they will be in equilibrium. The best example is, right, the best example is your ice and water, or when you have a boiling water, just keep a lid on that, right? Just keep a lid on that. What will happen? Just think about this. What will happen? It will convert into water vapor, yes. It will go up and strike on the lid, right? And then it will condense and again convert back into liquid. Yes or no, right? Okay, so obviously that is the case of equilibrium. Okay, right? That's it. Okay, everyone. So this we have already studied, right? So these are the basic, again, solid liquid equilibrium, liquid gas equilibrium, and all those things. Okay. So when we talk about equilibrium, right, the first thing that we know, reversible reaction. Second, concentration. Okay. Now, according to definition, I am saying that rate of reaction is, right, rate of forward reaction should be equal to rate of backward reaction for equilibrium. Okay, right, everyone? So when we talk about the characteristics of equilibrium, see, we have certain characteristics. First, it is dynamic in nature, yes or no, right? By dynamic in nature, I mean that the rate of forward reaction is equal to rate of backward reaction. The reaction is carried out. Okay, it's not that the reaction is stopped. Okay, reaction is always carried out. Reaction is not going to stop, but still there will not be any change. Okay, that is the meaning of dynamic in nature. Okay, the second, reaction should be reversible, means it should proceed in both ways. Okay, right? Now, at equilibrium, again, we are repeating all the concepts. Ultimately, it's only one thing. Rate of forward reaction is equal to rate of backward reaction. The concentration will not change. The third point represents the concentration do not change after equilibrium, unless and until we make some changes. Okay, right? So, if an equilibrium is achieved, it will try to attain the equilibrium position unless and until we try to change it. Okay, right? We'll study how we can change it. Now, fourth point, equilibrium is not affected by the presence of catalyst. Okay, now if you add catalyst, right, it will only change the rate. Okay, means the reaction will be faster or slower, but equilibrium will not be changed. Equilibrium may attain earlier or it may attain later, right, but the state will not change. Okay, right? The last change, again I said, right, unless and until any changes being occurred, equilibrium position will not change, right? But the change in pressure, temperature, concentration, or anything, right, can change the equilibrium position. Okay, so we'll discuss about the fifth point in detail. We have a next topic, right? Now first we will understand what is the basic definition of rate of a reaction. So just think about this, right? When we talk about rate of a reaction or rate, what's the basic definition of rate? Tell me what can we say about the basic definition of rate? It will be change in concentration with respect to time. Yes or no? Tell me, everyone, right? Okay, change of what? Concentration. Okay, what's the meaning of concentration? Tell me, everyone. Concentration means molarity, normality. Yes. Okay, right, everyone? Now, when we talk about rate, it should be positive. Yes or no? When we talk about rate, it should be positive. Okay. Now, what do you think? The concentration of reactant, it is decreasing or increasing? Tell me. Reactant concentration is decreasing or increasing? decreasing. So C2 minus C1, C2 minus C1, right? C2 minus C1 will be positive or negative? Tell me. It will be negative, right? So obviously, if you want to make this term positive, you have to multiply with a negative sign. Yes or no? Right? Got it? Okay, right? So obviously minus dc by dt, it just suggests that the concentration of reactant is decreasing, but rate of reaction should be positive. That's why we just multiply by negative sign. Okay, everyone? Understood, everyone? Tell me, understood? Okay. Now, what about rate of product? So suppose I'm just writing like this: A gives B, right? So at equilibrium, I'm saying that rate of forward reaction. So when we talk about rate of forward reaction, so we know that rate of reaction depends on reactant. Yes or no? Yes or no? Right? Rate of reaction will depend on reactant. Okay, right? Obviously, rate of forward reaction will depend on reactant. So I can say that rate. Okay, I'll just explain everything. Okay, first. Okay, let's see this. So I said that suppose I'm having a reaction A gives B. Okay, everyone, A gives B. So I'm saying that rate of forward reaction will be equal to, tell me what it will be. Tell me, will it be minus the concentration of A by dt? Yes or no? Yes or no? Yes. In the same way, rate of backward reaction it will be equal to d concentration of B by dt. Yes or no? Right? Okay. Because concentration of B is increasing now, right? Concentration of B is increasing, right? Okay. Okay. Now, if it is decreasing, we can just put minus, it's fine. Okay. Right? So I can say that, right? Rate of a reaction, okay, depends on concentration of reactant for forward reaction and concentration of product for backward reaction. Yes or no? Right? So there is a law called as law of mass action. Law of mass action. Mass action. Okay, that's a very important law, right? So what does this law says? Okay, everyone just pay your attention here. Okay, so suppose I'm having a reactant. Okay, right? I'm having a reaction. I'll just write it like this: alpha A plus beta B gives gamma C plus delta D. Right, everyone? Okay, so what is alpha, beta, gamma, delta? Tell me, what is alpha, beta, gamma, delta? What can we say about alpha, beta, and gamma, delta? What are they called? Everyone remember this? What are they called? Anyone? Stoichiometric coefficients. Yes, Siddharth. Very good. They're called as stoichiometric coefficient. Okay, stoichiometric coefficient. You have studied the first chapter. The first chapter was stoichiometry, right? How can you forget, right? It is the constant which tells us about how many moles of A should react with how many moles of B to give how many moles of C and how many moles of D. Yes, everyone? Right, everyone? Okay. So alpha, beta, gamma, delta is your stoichiometric coefficient. Now, law of mass action say that, right? Law of mass action say that rate of any reaction, rate of reaction is directly proportional to, again, directly proportional to concentration of reactant. So here, if you talk about forward reaction, reactants are, tell me, if you talk about forward reaction, what are the reactants? A and B. Yes or no? Agree? A and B? Everyone agree? Now, raised to the power coefficient, raised to the power of coefficient, right? I'm just writing coefficient A and B. See, A and B. Now, A and B can be equal to alpha and beta, right? Again, just remember this because this is something that we have to study in next year, right? In class 12. So for now, right? For now, you just understand, right? A and B may be equal to alpha and beta, right? Okay, depending on reaction, okay, right? But for us, we will take, right? For us, usually we will have A and B equal to alpha and beta, but it may be equal to, may not be equal to, because, right? I'll just name a term here. Do not think more about that because this term we have to study in next year. Alpha and beta are called as our molecularity. Molecularity, okay, means the number of molecules or number of atoms which is reacting. Okay, that is your alpha and beta. Okay, right? But A and B, A and B, right, are order. Now this is your experimental terms. Okay, right? Alpha and beta are your experimental terms. Okay, got it? It is directly proportional. Yes, no, it is directly proportional, right? If concentration of A is more, then the reaction will be faster. Yes or no? Got it, everyone? Tell me. Okay, right? So this is something that you just have to keep in your mind, right? Even if you don't get it, no issues in this. Okay. So why I'm telling this? Because sometimes if you encounter anything in which A and B is not equal to alpha and beta, so you should not be confused. Okay, everyone? Okay, very good, everyone. Very good. Okay, so what happened? Okay. Huh. Okay, so this is rate of forward reaction. So I'm just saying rate of forward reaction. Okay. Now, in the same way, I can say that rate of forward reaction. Now, since it is a proportional to, we should have a proportionality constant. Yes or no? Tell me. Should we have proportionality constant? Message everyone. Yes or no? Yes, very good, everyone, right? So we should have a proportionality constant. Okay, we should have a proportionality constant. So let's keep a proportionality constant. So this is called as rate constant. Okay, we will write it as K. Okay, K. Now since it's a for forward reaction, so we'll write it KF, right? Means rate constant for forward reaction. And then we have concentration of A to the power A, whereby concentration of B to the power B, small b. Got it, everyone? So this is the rate of a forward reaction according to law of mass action. Okay, so law of mass action says that rate of any reaction is directly proportional to its active mass. Okay, here I'm using the term active mass. Active mass, right? So active mass can either be concentration, or pressure or mole fraction. Okay, right? It can either be concentration or pressure or mole fraction. So active mass is basically the quantity which is changing. Okay, got it, everyone? So we will take active mass either concentration or pressure, right? Mole fraction we won't be considering because it's not in our syllabus, but Usually we'll take active mass as concentration and ratio. So here I'm taking concentration. Okay, so you might ask, so when we take ratio, so obviously it will depend on reaction. Okay, so if we have a gaseous reaction, there only we can take pressure. Yes or no? Tell me. Yes or no? Can we take pressure when we have aqueous reactant product or solid reactant product? Tell me. No, right? Okay, very good. So what do you think? What do you think? Tell me what would be the rate of backward reaction? Backward reaction. Tell me, what would be the rate of backward reaction? Everyone, message. Again, active mass is just a term. It's just a quantity which will change. Okay, in reaction, what is changing? Tell me. In reaction, what will change? Either concentration will change or pressure will change. Yes? Okay. Yes or no? Tell me. Right? So I just coined that term as active mass. As simple as that. Okay? Okay. So what would be the rate of backward reaction? Tell me, everyone. What would be the rate of backward reaction? Yes, very good, Ovas. Very good, Anisha. Anisha, you missed this powers, okay? So it will be KB, right? For backward direction, concentration of C to the power small c, whereby concentration of D to the power small d. Yes or no? Tell me, yes or no? Everyone understood this? Yes, very good, everyone. Okay, very good. Okay, now I said at equilibrium, rate of forward reaction is equal to rate of backward reaction. Yes or no? Tell me. At equilibrium, rate of forward reaction is equal to rate of backward reaction. Okay. Yes. So let's make this equal. Let's make this equal. Let's see what we can get. So rate of forward reaction, Kf is equal to concentration of A to the power A into concentration of, sorry, Kf into B to the power B. This is rate of forward reaction. This is equal to rate of backward reaction, which is Kb to concentration of C to power C into concentration of D to the power D. Yes or no? Tell me, yes or no? Everyone is getting this? Yes? Okay. I hope everything is clear till this point. Now tell me here, what are the constants? Tell me, what are the constants? Tell me, everyone, what are the constants? Kf and Kb are constants? Yes or no? Right? Kf and Kb? Okay, so I will just cross multiply and I'll write like this. Kf by Kb is equal to concentration of C to the power C into concentration of D to the power D divided by concentration of A to the power A into concentration of B to the power B. Yes or no? Tell me, yes or no? Agree? Agree? Okay? Okay, everyone, very good. Now, constant divided by constant can be termed as another constant, right? 2 constant, 5 constant. 2 by 5 is also constant. Yes? Okay? Okay. So if I'm taking active mass as concentration, say here I'm taking active mass as concentration. So I just coined this constant as Kc. C means concentration. Okay? Okay, everyone? Yes or no? Yes or no? Right? Get this? Now this constant is at which state? Right? At which state? At equilibrium? Yes or no? At equilibrium? So can I say that this is called as equilibrium constant? Equilibrium constant. Got it? Got it, everyone? Tell me, got this? Yes? Anyone have any issue in this? Tell me, anyone have any issue in this? Crystal clear? Okay, very good everyone, very good. See, if you actually try to understand each and every concept, everything would be easy, okay? Right? Just try to think about this. Now, my question would be, so you said that this ratio, this is what? This is concentration of product. I'll just write it like this. Concentration of product, right? Or product of product, product of product. Product means multiplication now, right? Okay, raised to their stoichiometric coefficients. Okay, raised to their stoichiometric coefficients. I'll just write it as S divided by concentration of product of reactant. So here product means multiplication. Okay, this first product means multiplication raised to their stoichiometric coefficient S1 S2. Okay, now my question is, okay, if this ratio is at equilibrium, if I'm considering this ratio at equilibrium, it is called as equilibrium constant. But what if I calculate this ratio at any other point, at any other time except equilibrium? Okay, what this ratio will be called? So this is called as Q. Okay, so I can say that, okay, concentration of C divided by concentration of D. Okay, there the concentration of A to the power A, the concentration of B to the power B is equal to Q at any other point of time except equilibrium. Got it? Got it everyone? Tell me, got this, yes or no? Right? Kc is only at equilibrium. Kc is only at equilibrium. Okay, right? But if you want to calculate this ratio at any other point, it is called as Q, which is reaction quotient. Reaction QUEI. I'm horrible in spellings, by the way. Okay, so please pardon, right? If I'm writing wrong spelling, right? Just let me know. It's wrong spelling, I guess. Okay, it's quotient. Okay, reaction quotient. Okay, everyone, got this? I hope everything is clear here. Everything is clear till this point? Yes? Okay, very good, everyone. Okay, very good. Okay, now I'll just try to write the summary. So I can say that for any reaction, right? A, or alpha, I'm writing A, right? So I'm saying that in this stoichiometric coefficient and order are same. Okay, it's an elementary reaction. So AA plus BB gives CC plus DG, right? So here I say that Kc is equal to concentration of C to the power C into concentration of D to the power D by concentration of A to the power A, concentration of B to the power B. Yes or no? Yes? Okay. Now just suppose, right? Instead of concentration, okay, right? Instead of concentration, I have taken ratio, right? Now instead of concentration of A, I have taken pressure of A, partial pressure of A, right? Partial pressure of B, partial pressure of C, partial pressure of D. Okay, right? Suppose. Okay, now before asking this, let me ask you, this concentration of D, right, is at equilibrium or initial concentration? Tell me. It will be at equilibrium or initial concentration. The concentration that I'm taking over here, right, is at equilibrium or initial? Tell me. Tell me, everyone. Yes, exactly. No, Amish. We are taking equilibrium concentration. Okay. This is one thing that you should remember, right? When you talk about Kc, it is equilibrium constant. So the concentration is also at equilibrium. Okay, everyone? Right? So the active mass that we take should be in equilibrium. Now just think about this. Just think about this. Now instead of taking active mass as concentration, I'm taking as partial pressure. Okay? Right? I hope all of you remember partial pressure. Tell me yes or no. All of you remember partial pressure? Anyone who doesn't remember partial pressure? Everyone remember, right? So can I write like this? Just think about this. Can I write like this? Partial pressure of C, right, to the power C into partial pressure of D to the power D divided by partial pressure of A to the power A into partial pressure of B to the power B. Can I write like this? Tell me. Yes or no? Yes or no? Because when we talk about law of mass action, I said it is active mass, right? That's why Chulika also asked that, so why it is different? Because you can use any of the terms. You can either use concentration or partial pressure. Now, what will this called? Will this be AC only or it will be something else? Tell me. What do you think? Just think logically, right? Intuitively, what it will be called? Yes, it will be called as Kp. Got it? It will be called as Kp because it is pressure, right? So it is called as Kp now. How it can be Kc, right? Tell me, is partial pressure of A equal to concentration of A? Tell me, is partial pressure of A equal to concentration of A? Yes or no? Just think about this. Is partial pressure of A equal to concentration of A? No, right? No, no. Right? Okay, so obviously, right, Kp should not be equal to Kc all the time. It may be equal in some cases. Okay, right? Now I give you a small homework, not homework, small class work. I will give you 2 minutes, right? I hope all of you have observed this. I'll give you 2 minutes, right? Find relationship between Kc and Kp. Everyone, find relationship between Kc and Kp. I'm giving you 2 minutes. Okay, everyone? Okay, I'm giving you 2 minutes. Just try. Everyone should try. Okay, I'm giving you 2 minutes. Okay, everyone. So I guess you guys have tried something. So let's see. Okay, let's see. So we know that we'll start with the relationship between pressure and concentration. So tell me, what is the relationship between pressure and concentration? How many of you remember this? P is equal to CRT. Tell me, how many of you remember this? P is equal to CRT. Everyone remember this? So can I say that partial pressure of A is equal to concentration of A into RT? Yes? In the same way, partial pressure of B is equal to concentration of B into RT. In the same way, partial pressure of C is equal to concentration of C into RT, right? And partial pressure of D is equal to concentration of D into RT. Yes or no? Tell me, yes or no? Everyone agree? Everyone agree with this? Yes, okay. So let's see. Let's put the value here. Let's put the value in Kp. So can I say that Kp is equal to, what is the partial pressure of C? Just put the value partial pressure of C. This concentration of C, right, into RT to the power C, the power C, right? Now into partial pressure of D, which is concentration of D RT to the power D. Yes or no? Yes or no? Agree? Tell me everyone. Do you agree? Yes. Very good everyone. Very good. Okay everyone. Now in same way, I can say that partial pressure of A can be written as concentration of A into RT to the power A. Yes. Yes everyone. Very good. And partial pressure B is concentration of B into RT to the power B. Okay. Now let's see here. We can see that RT is a constant, right? Because obviously when you talk about equilibrium, right? Equilibrium is attained at constant temperature. Yes or no? Equilibrium is attained at constant temperature. Okay. Right? That's something that you should remember. Okay. So I can take out RT from this expression. So I'll be having concentration of C to power C into concentration of D to power D, right, into RT to the power C plus D divided by concentration of A to power A into concentration of B to power B into RT to the power A plus B. Agree? Tell me, everyone agree with this? Screen is not blurred, Sneha. It might be internet issues. Okay, right? So, see this. If you observe this, what is this? Tell me. Wait, I'll just change the color. Okay, what is this? Can you tell me what is this? What is this? Is it Kc now? Agree? Is it Kc? Yes, very good. So, can I say that is Kc RT? Now, this is C plus D minus A plus B. Obviously, C, D, A, B should be gases, right? Yes, it will be stoichiometric coefficient of gases because we are taking gases here. Now, I hope all of you remember that number of moles of product, gaseous product, minus number of moles of, reactant, gaseous reactant is called as delta Ng. Right, everyone? Agree? Delta Ng. Anyone have any issues now? Tell me. Anyone have any issues now? So can I say that Kp is equal to Kc only when if delta Ng is equal to 0? Yes or no? Yes or no? Okay. And in the same way, Kp is greater than Kc if delta Ng is greater than 0. Right? So this is whole power of RT. Okay. And Kp is less than Kc if delta Ng is less than 0. Agree everyone? I hope all of you understood. Right? I hope all of you understood this. Yes or no? Yes, very good everyone. So I hope all of you understood this point. Very good. Now, there's a point which I need to mention. Okay, I'll just write it away. I've already told it, right? So you just sum up. Kc or Kp are constant, are equilibrium constant. And do not depend on active mass. Active mass, right? It depends only on, tell me, it depends on what? Temperature, okay? So it depends on temperature. Okay, so if you're calculating Kc or Kp at one temperature, right, or if you're calculating Kc Kp at another temperature, then Kc and Kp will change. But if you change the concentration of C or D or A or B, the Kc or Kp will be same. Okay, so what does that mean? It means if suppose if C or D is increasing, just imagine C or D is increasing, what should happen to A and B? Tell me, if C and D is increasing, what should happen to A and B? Yes, it should also increase because the ratio is constant. Okay, very good, everyone. So that's the meaning of Kc and Kp. So this is star mark point. You have to remember this. Okay, right, everyone? Okay, everyone. Okay, so let's see this. Okay, I hope all of you already understood this. So rate of reaction, we understood what is the rate of reaction. So in case of reactant it is minus, in case of product it is plus. Okay, okay, right? So the concentration change may be positive, may be negative, as I said, but rate of reaction is always positive. When you talk about the unit, obviously it's concentration per time. Okay, now depending on, obviously it is depending on what you are taking, either pressure or concentration. If you're taking concentration, it is mole per liter per second. If you're taking pressure, it is Pascal per second. Okay, so it totally depends on the reaction. Okay, everyone, I'll just revise what you have studied. Okay, so see, we studied that if we have a reaction A plus B gives C plus D, then rate of forward reaction is Kf into concentration of A into B. So here we haven't taken the, here it is not the coefficients, right? The reaction coefficients, stoichiometric coefficient is not taken. That's why it is said that for unitary stoichiometric coefficient. Okay, for unitary stoichiometric coefficient. So we'll just see the stoichiometric coefficients, one with stoichiometric coefficients. Okay, so let's see, one with non-stoichiometric coefficient will be better, right? So for non-stoichiometric coefficients, we had this relationship of K equilibrium, right, everyone? Everyone agree with this? Okay, see, as I said, it represents active mass. It can be taken as molar concentration or pressure or mole fraction, but we will be studying only pressure as well as concentration, molar concentration, right? Okay, everyone. Okay, so we are done here with the theory part. We'll try to solve some problems, but before that, okay, right? Before that, I will try to explain how to find the Kc and Kp. What kind of question will be given? Okay, so let's see. Right, everyone, just take out your notebook, right, and just try to solve this problem along with me. Okay, right, step by step. Now, if you talk about the numerical, right, just ask yourself what kind of question can be asked. Okay, so suppose I'm just taking an example, right? Question 1. This is a very famous reaction that you will study, very famous reaction. Suppose I'm having this NH3 to NH3, okay, gives N2 plus 3H2. This is a reversible reaction, right, everyone? Okay, agree? Now, first step, this is your first step. Step 1, write down balanced chemical reaction. Write down balanced chemical reaction. Okay, that's your first step. Okay, everyone, write balanced chemical reaction. Balanced chemical reaction. Every time when you try to solve a problem, first step should be write a balanced chemical reaction. Second step, Suppose initial concentration of NH3 is A. Of N2 it would be 0, H2 it would be 0. If it's not given, right? Obviously, if it's given, it would be something. But here I'm taking that initial concentration of A is this, right? Initial number of moles. Okay, initial number of moles. It can either be concentration or mole, by the way. We can just convert it later. Okay, so second step, this is step 2, right? The initial concentration. Now, what do you think? At equilibrium, NH3 will be consumed, yes or no? Tell me. At equilibrium, NH3 will be consumed. Tell me, yes or no? Yes. So suppose it is consumed by X amount. NH3 is consumed by X amount. How much N2 will be formed? Tell me, how much N2 will be formed? Everyone. The ratio, how can you forgetting principle of atomic conservation? 2:1:3. If this is A, right? If this is 2A, then this should be A, then this is 3A. Now I'm saying that this is consumed X, so this should be X by 2, na? Right? Yes. Ratio, you have to consider the ratio. Okay, that's the third step, X by 2. And what is the amount of H2 formed? It will be 3 into X by 2. Agree? Tell me. This is a step 3, right? Step 1, write the chemical reaction. Step 2, write initial concentrations. Step 3, write concentration at equilibrium. Okay, now see. This is at equilibrium. This is at equilibrium. Now here, it may be moles or concentration. Okay, right? Means, see this. I'm taking A. A can either be mole or it can be concentration. What's the difference? If A is mole, then concentration should be what? A by total volume. Yes or no? Tell me. Yes or no? Yes or no? Tell me. Yes. So here I'm taking moles. Initially I'm giving moles, right? And the total volume is V. Yes or no? Because reactions carried out in a same vessel, right? So volume of NH3, volume of N2, volume of H2 should be same. Yes or no? Right? Agree? So concentration of NH3 should be what? Concentration of NH3 should be A minus X by V. Concentration of N2 should be X. X by 2V, and concentration of H2 will be 3X by 2V. Agree or not? Agree or not? Yes or no? Tell me. Agree? So I hope all of you understood till this step 4. Anyone have any issue till this step 4? Anyone have any issue? If it would have been concentration, I would have stopped till third step, right? But since it may be in number of moles, so I have to divide by volume, okay? Because I need concentration. So since here we have concentration, I can say that Kc is equal to what? Tell me, what is Kc? It is concentration of product raised to their stoichiometric coefficients. So concentration of N2, write down this, N2 to the power 1 into concentration of H2 to the power 3 divided by concentration of NH3 power 2. Write it like this first. Okay, this is your step 5th. Right? Now we know that. What is this concentration of N2? It is X by 2V. So X by 2V to the power 1. Agree? What is H2? It is 3X by 2V to the power 3 divided by, what is this? It is A minus X by V to the power 2. Agree, everyone? Agree? Anyone have any doubt till this point? Tell me, anyone have any doubt till this point? No? Very good everyone, very good. So let's simplify this. So after simplifying, we will get like this now. X into 27x will be 27x cube, 27x cube, right, by 2 into 4, sorry, 2 into 8, 16, 16 into a minus bx whole square. Now volume term. So in numerator we have 1 by v to power 4, in denominator 1 by v square. So we'll have 1 by v to the power 4 minus 2. Yes or no? Tell me, right? In numerator we have power 4, in denominator we have power 2. So it is 1 by v to power 4 minus 2. This is 27x cube. Sorry, x power 4. Sorry, my bad. It is x power 4 now. X power 4. X power 4. Yes, my bad. By 16 a minus x square into 1 by v square. As simple as that. Everyone got this? Yes? Tell me, yes? Okay, okay everyone, right? So we will end our class. Okay. So this is for KC. Wait, I'll just complete KP also. So this is for KC. So I hope all of you understood how to find KC. Yes or no? Anyone have any doubt in KC? So these are the steps to find KC, step by step. 5 steps you will get KC. Now we will see the steps to find KP. Okay? Steps to find KP. Okay, so same till step 3. Same, okay. Same as KC till step 3. Everything we should do same till this point. Till this point, right? Everything should be same. Okay, you have to write the reaction, you have to write initial number of moles, you have to write number of moles at equilibrium. Okay, tell me, yes, agree? Tell me, agree? Anyone have any issues in this? Okay, now things will change after step 3. Okay, yes, Siddharth, you can write like this, you can find radically, okay, but there's another method also. Okay, sometimes you cannot find. See, so there's a method 1, right? Method 1, just to use this formula, Kp is equal to Kc RT to the power delta Ng. Right? This also you can use. But if temperature is not given, you cannot use that. Okay, right? So sometimes you just have to calculate like this. Step 4, find N total, right? So tell me, what do you think? What is N total at equilibrium? Tell me, what is N total? Total number of moles at equilibrium. Everyone, what is total number of moles? It is A minus X plus X by 2 plus 3X by 2. Yes or no? Yes or no? Right? So N total at equilibrium, it is A minus X plus X by 2 plus 3X by 2, which is equal to A plus X. Yes? Okay. Now, there's one more thing which is given. In this, right, what would be given? P total at equilibrium will be given. It will be given, right? So tell me, what is partial pressure of A at equilibrium? Tell me, what would be the partial pressure of A? Sorry, not A. Here we have NH3 now. So tell me, step 5. Partial pressure of NH3 at equilibrium. Tell me what it would be. What do you think? What is the formula of partial pressure? In states of matter we have studied, right? What is the formula of partial pressure? It is mole fraction of NH3 into P total. Yes or no? Yes or no? Right? What is mole fraction of NH3? It is number of moles of NH3, which is A minus X. Number of moles of NH3, which is A minus X. And now at equilibrium, thereby total number of moles, which is A plus X into P total. Agree? Agree, yes or no? Tell me. Agree? So, in same way, can we find Pn2 and pH2? Tell me, what is Pn2? Tell me, what is Pn2? Will it be x by 2, right? Thereby A plus X into P total. In the same way, for pH2, it is 3x by 2 A plus X into P total. Yes or no? Agree, everyone? Agree? Step 5. Okay, step by step, don't worry, right? We did the same thing. Now, step 6, which is last step, just put the formula. Pressure, partial pressure of N2 to the power 1 into partial pressure of H2 to the power 3, thereby partial pressure of NH3 to the power 2. Just put these values here, you will get Kp. Okay, now since here I'm taking the terms, right? I'm not taking the value. That's why it seems a bit complex, but you would be given values. Okay, everyone? Tell me, okay? Understood how to find Kp and Kc for any given reaction? Okay? Okay, everyone. Now there's one important point, star mark, right? We will end with this point. Active mass of pure solid and pure liquid is always taken as 1. As 1, always. Okay, always, right? Means the change of concentration for pure solid and pure liquid will not affect the equilibrium. Okay, we will explain why in next class. Okay, everyone, so that's it. That's it for today's class. Okay, bye everyone. I hope you enjoyed today's class and understood each and everything. Just raise your hand. You understood each and everything? Very good. So what you should do after this class, before Wednesday class, you should watch this 7.1 and 7.2 videos. Okay, everyone? Right? Okay. Bye, everyone. Right? Okay. Bye, everyone. Bye, bye. Bye, bye. Bye, bye. Okay. Bye, everyone.
Thank you, sir.